In addition to boiling point elevation and freezing point depression, solutions also exhibit an osmotic pressure. We can use this property of solutions to measure the molar mass of large molecules like polymers and proteins, and so it may be useful to understand what osmotic pressure is and how it's related to the chemical potential. If we have a U-tube in which the bottom has a semi-permeable membrane such that solvent can cross the membrane but solute cannot, and we fill one side of that U-tube with the solution and one side with pure solvent, what we will find is that the solvent is going to travel from the pure solvent side of the U-tube to the solution side of the U-tube, making the volume in the solution side higher than the volume in the pure solvent side. The difference in heights causes a difference in hydrostatic pressure on either side of the U-tube. This difference in height or difference in pressure is what we call the osmotic pressure. When the system comes to equilibrium and the heights have stabilized, we know that the chemical potential of the solvent in the solution is equal to the chemical potential of the pure solvent. We can use this fact to derive an expression for the osmotic pressure. Because the pressures on the two sides of the U-tube are not equal, we will need to think about how the chemical potential changes with pressure. Remember that the chemical potential changes with pressure at a given temperature as the molar volume of the solution. If we separate variables, d mu is equal to the molar volume dp, integrating both sides of this equation from the standard state to any other state will give us a general expression for how the chemical potential changes when I change the pressure. So the chemical potential at any pressure minus the chemical potential at the standard pressure is equal to the molar volume of the solution times the pressure minus the standard pressure, where here we've treated the molar volume as approximately constant with pressure because molar volumes of liquids and solids do not change much with pressure. When our osmotic pressure U-tube comes to equilibrium, we know that the chemical potential of the solution, which is at P2, is equal to the chemical potential of the pure solvent, which is at the pressure exerted by the pure solvent. The chemical potential of the solvent in the solution at P2 is equal to the standard state chemical potential for the solvent plus the molar volume of the solution times P2 minus P standard plus a correction for the fact that the solvent is not pure. The chemical potential of the pure solvent at the pressure exerted by the pure solvent is equal to the standard state chemical potential plus the molar volume of the pure solvent times the pressure exerted by the pure solvent minus the standard pressure. And what we're going to do is equate these two because we have equilibrium. So when we equate those two, a number of terms will drop out. The standard state chemical potentials will be equal, and so we can cancel those on both sides. The molar volume of the solution times the standard pressure and the molar volume of the solvent times the standard pressure are essentially the same because we have a dilute solution, and so those terms will cancel out on both sides of the equation as well. This leaves us with the molar volume of the solvent times P2 plus RT, natural log of X of the solvent, is equal to the molar volume of the solvent times P exerted by the pure solvent. Rearranging this equation leads to the molar volume of the solvent times P2 minus P pure is equal to minus RT natural log of X of the solvent. The natural log of the mole fraction of the solvent is equal to the natural log of 1 minus the mole fraction of the solute, and we can approximate that as equal to minus the mole fraction of the solute. Making that substitution, the molar volume of the solvent P2 minus P pure is equal to RT times the mole fraction of the solute. Notice that this difference in pressures is exactly what we call the osmotic pressure, and we give that the symbol pi. And so we can write that the osmotic pressure is equal to RT x solute divided by the molar volume of the solvent. In dilute solution, the mole fraction of the solute is equal to the number of moles of the solute divided by the number of moles of the solvent. Making this substitution, the osmotic pressure is equal to RT times the number of moles of the solute divided by the molar volume of the solvent times the number of moles of the solvent. But the molar volume of the solvent times the number of moles of solvent is just the volume of the solvent. And the number of moles of solute divided by the volume of solvent is the concentration in moles per liter of the solute. And so we can write that the osmotic pressure is equal to RT times the concentration of the solute in solution. And that is our final expression for the osmotic pressure.